All right, welcome back. This week we are covering pumps and motors. There's a lot to cover on this presentation, so I'm going to split it up for you. So let's dive right in. All right, so this week we're going to cover the common uses of pumps in our industry, how do they work, the different types of classes, how they operate, and some maintenance considerations. So as you can see from this slide here, pumps are used in many different ways, right? So really you're pumping from a lower elevation to a higher elevation. You're trying to increase pressure into a zone, but water, is generally moved from a lower elevation to a higher elevation or from a lower pressure into a higher pressure zone. So like I said on the previous slide, here's some other examples that are kind of spelled out for you. Treated water that's delivered from wholesalers to distributors. Chlorine injection systems use a booster pump. Large capacity storage tanks that have to meet both the supply and the demand requirements. Um, there's just a series of pump stations and reservoirs that deliver water to a higher elevation. But yeah, there's a ton of different ways that pumps are used throughout our industry. So generally speaking, there are two basic categories of pumps. You have a positive displacement pump, and then you have velocity pumps. The pump that you elect to use, there's a lot of factors that go into selecting the style of pump that you're going to use, and it all just depends on what your needs are. But generally speaking, pumps fall into these two categories. So how do these work? You've got a positive displacement pump that makes fluid move by trapping a precise amount of water and forcing or displacing that trap volume into a discharge pipe. Um, you'll see this, you've heard of like positive displacement meters. And so it's generally the same. It's a measured amount of water that is used repeatedly and flows through this, in this case, a pump. And then you have velocity types, which is an impeller type of pump that converts shaft power into fluid power and then increases the angular momentum of the flow. So let's dive into some of this stuff and so that way you could see it in motion. So first, when talking about positive displacement pumps, you have a couple different types. You have the piston type, the rotary type, or the lobe and gear, which I've got a few examples coming up, and you'll see what I mean. They're used primarily for chemical injection, so like at a treatment plant, or like if you have some kind of on-site generation or chlorine booster station to increase the residual in your system. That's, because you want to measure that amount, right? That needs to be a specific amount of chlorine that you're pumping out in your system. You can't, have that uh, be a guess. But then also you cannot start those against closed valves because it will create what's called overpressurization and lead to either your pump breaking or your main line blowing out. So you got to be certain that the downstream valve is open. Okay, so as water or liquid fluid comes in to your pump casing here, this shaft here is moving in this direction, which is creating that suction, right? So it's coming in and filling up this cavity here. And then as the shaft here pushes in this direction, it is forcing or displacing that liquid out this direction, right? So you can see it comes in, this as this is pulling away, and then as it comes back, it pushes it out, right? So that's generally, how your positive displacement pump is working. Here you can see this is the piston type, and as this shaft moves back and forth, it's going to take water from either side of these check valves and pull water in, and then to just push that water out, right? So this is just a different type of cavity, different kind of setup. You got some packing glands that you could see on here, but as this shaft rotates around, it's causing this to pump this piston, right? Is going back and forth and using a calculated amount of water. Okay, so here you can see it in motion, right? So as this crankshaft is spinning around, it's driving this piston back and forth, And as that piston comes back, it's sucking water in, and then as it moves forward, it's pushing water out or displacing that water. Um, so this is, a relatively good graphic on how a positive displacement pump works. So like I mentioned before, we've got the two different type of rotaries. We got the gear type. As you can see, this looks like a gear. So as this is spinning around this direction, this one's spinning around this direction, it's forcing water into the outside of this cavity. And then over here, same thing, right? You've got a lobe type, right? So this is, looks like lobes, almost like your earlobes, right? And as this spins, it too forces water into the outside of this cavity and then pushes it out. Um, so I think I got a graphic of that one too. So before we get into the graphics, just some notes on rotary type pumps is that they have a self-priming property to them. And due to that self-priming property, these pumps are able to pump liquid as well as gases. However, you got to make sure that you're not pumping any types of solids, right? Because the abrasive materials entering pumps can damage the helices and clearances of the pump. Um, but all types of rotary pumps continue to force liquid into the system regardless of their opposition to the transfer. So anyone who's ever, like worked out in the field and you have a diaphragm pump, I'm sure you can appreciate the fact that a pump has a self-priming property to it. That's really appreciated. Okay, so here I've got a list of advantages and disadvantages, but just to kind of touch on a couple of them, rotary type pumps have a wide range of liquids and viscosities. Viscosities is the thickness, if you will, of the fluid or liquid, right? They have high speed capabilities. Again, that self-priming is a key thing. Um, they have a high tolerance for entrained air. So, like I said before, anyone who's ever worked with the diaphragm pump, you know that the moment you get air inside of there, it's, losing uh, its suction and its pump. But there is high cost associated with these, and they can be very large in size. So here you can see this is a lobe type rotary pump. As the water comes in, or the fluid, liquid, whatever you want to call it, gas, as it comes in, you can see that it's being forced to the outside of that pump casing before it's being distributed or displaced out into the system. Again, you can see how close those lobes are to the outside of that casing, right? So that's like those clearances that we were talking about earlier. Very tight, and that's why you can't have solids going through this type of pump. So the most common type of velocity pumps are centrifugal. Um, so you might see that question on an exam, but horizontal or vertical, right? So you can have those pumps oriented in different ways. Just depends on what you're trying to accomplish, what kind of space you're working with. But they both use the principle of centrifugal force to impart energy into water. So in the water industry, velocity type pumps are primarily used in distribution systems. They have the ability to convert velocity head into pressure head. What does that mean? That means that you're able to take this small amount of head pressure that you have on your pump and convert that into pressure head, meaning you're able to pump it to higher elevations, into higher pressure zones. And so that's primarily what you're going to find out in the water industry distribution systems. So as that velocity pump spins that impeller, it accelerates the water to a high velocity, right? So if you don't already know, there's this inverse relationship between velocity and pressure, right? You either have a high velocity and low pressure, or you have low pressure and high velocity. That's just the relationship between the two, right? So as that pump casing channels that water through the area of the increasing cross section. It increases the cross section, causing velocity to decrease while pressures increase, right? So as water's flowing through there, it's increasing that velocity. And then as it's being discharged, you're flowing it into a smaller area, which then increases that pressure, right? One of the other advantages to a velocity pump is that it can be started against a closed valve, right? And that's typically what you need to do. So you have they call like a foot valve or an auxiliary valve that's right downstream of that pump. And as that pump turns on, it pushes against that valve and it causes it to slowly open, right? Um, and one of the advantages to that, of course, is you're preventing water hammer. So as that valve is slowly opening, then that water is being discharged out in the system, increasing the pressures, and going out into the system. So here you can see water is drawn into the eye of this pump, and then it is basically thrown, if you will, to the outside of this casing, and it travels around the casing and then discharge out into the system. Um, so here are the parts as well. As you can see, you've got a rotating impeller, you've got your shaft. The volute is what is called for on the casing. So water is thrown off the impeller due to centrifugal force, right? And so these are just, it's a nice little schematic of how this type of pump works. And here it is in motion. So you can see as water is pulled through the eye of that impeller, and then you have the vanes of that impeller that are discharging it or throwing it to the outside of that volute. That water travels around, increasing in pressures, and then being discharged out into the system. When you're talking about velocity pumps, there's different impeller designs because it depends on the what you're trying to pump. Right? So you can have it for this radial, axial, or mixed flow design. And it like again, it just depends on what it is you're trying to pump. And so the impeller that you select is just as important as the type of pump that you're selecting. But they can be used for a broad range of heads and capacities. In the radial flow design, you can see how water is pulled into that eye of the impeller, and then it is discharged by the vanes into the volute and then discharged, right? So you've got this radial flow design. With the axial or propeller flow design, there's a couple different ways that you can achieve your pumping goals. One is that you're sucking water up uh, through this strainer into the foot valve, and then as it discharges, you hit this eccentric reducer. What an eccentric reducer is that one side will stay, I guess, horizontal, if you will, in this case, which is this top part, whereas this bottom part, as you can see, is coming in at an angle, and that's what's going to help give it that direction of flow. So the other would be a concentric reducer, which is actually this one right here. It's not labeled, but you can see that it concentrates out into a center point, right? Whereas the eccentric has only one angled side. But anyway, water travels through the pump and then out into your system. In this case over here on B, you can see that you got your propeller down here and it is sucking water up into well, this is your pump, right? This is water, just pulling it up and then discharging it directly out. Lastly, you got the mixed flow design. As water is pulled in, it is discharged to either side of this casing, and that's just to move more water. So if you needed to discharge a lot of water, that the mixed flow design provides that possibility. Um, but you can see water is pulled in, it's sent into the discharge side or the volute casing, um, and then discharged. Here's some other examples of these, just to help you see it if it's not quite making sense yet. But you can see with the radial flow design, water is brought in from one direction, discharged in a different direction. With the mixed flow design, you can see water's, you know, discharged in different directions before it's sent out. And then with axial, it's all kind of comes and flows in the same direction. Water's traveling in that same, in this top example here, like a horizontal direction. Couple different impeller designs. You can have them open or closed. With the open, it allows for slip, meaning that you're not pumping at such a high efficiency or with such preciseness, but it is good, because you can pump, liquids with solids in them. And so that's why you would want that openness because it allows for the passage of those solids. But then in the closed design or the no slip type, you definitely don't want to have any kind of solids. It is used for pumping at higher efficiencies. In these schematics here, you can see, I've said this a few times, vanes. These are the vanes of the impeller, right? So if you didn't know what I was talking about before, I apologize for not explaining it sooner, but these are your vanes, right? These are what's inside of that impeller that is directing that water, right? So in this case here, we've got an open impeller, right? Uh, y- you can see how solids are able to move through here and be discharged, whereas with a closed impeller, you don't have that option, right? The closed impeller would not be suitable for solids. But again, if you're trying to achieve high efficiencies, it's definitely the better impeller option. This is another schematic of a closed impeller. But water is pulled into the eye of the impeller, and then it is discharged into the vanes and then out into the volute of your pump. Get some more information on centrifugal pumps. They are typically horizontal in configuration. It's the most common setup for a centrifugal type pump. They use the volute, that expanding spiral. Um, they could be multi-stage, which we'll talk about later on. They can achieve high operating heads at good efficiencies. So you're talking like high 80 percentile for efficiencies. And these are designed to operate at a higher pressure with lower flow rates than the axial or mixed pump flow. And this is the schematic that we looked at earlier. But based on what we've talked about, now you can see how water is pulled into this eye of the impeller. You've got the vanes here of this impeller that are discharging that water into the volute and then discharged out into the system. And this is the radial style. Another good schematic to help it all make sense if it's not already. But water comes in, it is sent out into the vanes here through centrifugal force, and then into the volute, and then out discharged out into the system. This is schematic or an open cut of a split case pump, which would be the mixed flow design that we had talked about earlier. As you can see, this is super large pump. It can pump a large volume of water, but it also takes up a large space. So split case pumps are designed for double suction and they operate at much higher pressures. So like if you go inside, some of the county water authorities or some of the larger distribution systems, this might be the type of pump that you see operating there. And then with centrifugal pumps, you got your advantages and disadvantages, like I talked about with the others. They're compact, inexpensive. Design efficiency is 75 to 85%. So, like I said, if you can get them up into that high 80 percentile, you're doing all right with the centrifugal pump. And they can operate against a closed head. However, they are not self-priming. And so it's important that you prime these, which means if you don't know what priming is, it's where you would fill it with a liquid to push out any air, so that way you can avoid cavitation. If there's cavitation, then there's no liquid in those areas, and you're not going to be able to pump anything. But then they do have a suction lift of, approximately practical, as you can see here, 15 to 20, sometimes 25 feet. theoretically is that 34 feet. If you've taken the distribution math course, you know that to get that number, it is 2.31 times 14.7, and that's how you get like 33 point something, rounded up to 34 feet theoretically. Okay, so here you can see, you've got a horizontal configuration for a centrifugal pump, and it's actually connected to its electric motor. If you ever get the chance to go out into a pump station, you might see something similar to this. Not maybe not this exact setup, but like if you can recognize this configuration, you can understand that you've got here a centrifugal pump, and its motor. And so with that, I'm going to go ahead and stop this first video, and then we'll pick it up again with the next slide. All right.